Now that you understand the registers in general CPU architecture, let's look at the register from another perspective. So we can view the ARM processor from two perspectives. In the viewpoint of hardware, an ARM processor is nothing but the silicon. This image is coming from the foundry where the ARM processor is manufactured. In this case, there's nothing we can control the ARM processor from software perspective. And another viewpoint of the ARM processor is the architecture. This architecture means it is interface between hardware, silicon, and the software. So through the ARM architecture, the software can control the ARM processor. In Armv8-A architecture, we have various features in the architecture that include assembly instruction, the register, exception labels, virtual memory system, and trust zone, and so on. But when we make the ARM processor perform specific task, the unit of this kind of task is the execution of the machine code. As you know that this machine code can be mapped onto the assembly instruction. If you compile your own source code in C code, your compiler will generate machine code. With the machine code, we can generate the assembly instruction using corresponding disassembler. An important point is, before running any assembly instruction, it is necessary to check the value of the register, because most of the register is used as the input to run any of the assembly instruction. Let's suppose that assembly instruction is executed. At this point, what should I do to check the result of the assembly instruction? For this, we need to check the value of the register. So point is, most important features of ARM architecture, I believe that is assembly instruction is the register. Through the register, we can identify the status of the ARM processor. Through the register, we can set the necessary configuration of the ARM architecture. It's important to understand how the registers are organized. Now, let's analyze another example assembly instruction. And here, this assembly instruction is placed in the left corner. The label name is CPU switch to. This label is called every time context switch operation is performed in Linux kernel. And if you look at this assembly block, you can see that in each assembly instruction, you're going to see the general purpose register. Please take a look at this assembly instruction. This is the add assembly instruction. A value of the X0, value of the X10 register are added. Result is stored onto the X8 register. In this case, the register are used as input, and the X8 register is used as the result. So this register is called destination register, and those register is called the first operand, the second operand, and so on. And as for this assembly instruction, the value of the SP register is copied onto X9 register. As for this assembly instruction, the value of X21, X22 will be copied onto the target memory address. In this case, the base address for target address to store is X8 register. This value could be added to the X8 register to calculate target address to store. What I mean is, those two registers are stored onto this target address. As you can see, whenever you analyze any of assembly instruction, you're going to see that any of general purpose register. That is why it is important to understand how these general purpose registers are used in the software level.